Hello and welcome back to 5 Minutes of Postgres. My name is Lucas and today we're going to talk about distributed Postgres architectures. This is a blog post by Marco Slot on the Crunch Data blog. For context, Marco is the principal author of the Citus extension for Postgres, and he recently joined Crunch Data to continue working on distributed Postgres. Of course, ideally, we'd like to have all the benefits with none of the downsides. But oftentimes with distributed systems, one of the most important downsides, besides the cost of running extra hardware, is going to be latency. The best latency you'll get is if you don't distribute your system at all. Once you start distributing your system, you essentially step up a ladder of how much latency is acceptable to you. This oftentimes can be quite harsh for an application using Postgres, because most applications using Postgres work with Postgres in a sequential way, and Postgres itself many times works sequentially as well with the disk that it accesses. What this means is the more latency you have between your client and your Postgres, or your Postgres and another Postgres it needs to talk to, or the disk, the less throughput you will have, and the worse your application will perform, and the more frustrated your users will be. If we do distributed architectures, we should be very careful with which latency is acceptable to us in which situations. Marco starts by talking about the most basic form of distributed Postgres. Most Postgres servers in the cloud are distributed because underneath the hood, they use the block storage APIs by the cloud providers to store the data. And in that case, you do actually keep multiple copies of the data on different storage nodes. And so that means you are already paying a price of latency because you're saying, I want multiple copies, I want that network attached storage. There, you are already seeing the downside, which is on a regular NVMe drive, you'll get over 1 million IOPS quite easily and really low disk latency in tens of microseconds. But then once you go to the network attached storage like EBS, you get 10,000s of IOPS and you get much higher disk latency. But still, this is something that basically anybody in the cloud relies on in some way or form, which is they want the benefit of being able to take snapshots. They want the benefit of if the database server goes down, they can easily just start up another VM from the same block storage. This is a trade-off that many people accept. Now, there's two things worth mentioning in this context, though, which is, first of all, some of the cloud providers like Amazon have started doing what they call optimized reads. Optimized reads makes use of these NVMe drives that are attached to the servers and uses them for caching. That means in the cases where the information is locally in that NVMe drive, it's going to be much faster than going to the EBS block storage. That's one way you can get the best of both worlds, at least in some cases. The other improvement is that Postgres itself has a lot of work going on in the Postgres community around asynchronous I/O. The benefit of asynchronous I/O is that we're increasing the concurrency of our I/O requests. We're able to do more things in parallel, and that way we can make better use of a typical block storage in the cloud. Another component that most people that use Postgres at scale are using are read replicas. There's not much sense in diving too much into this, but let's just say if you can solve your problems with read replication, that's the best way to do it, right? Don't worry about distributing Postgres in any other way. If your bottleneck is reads, read replicas are the way to go. They're the easiest way to scale out Postgres and keep it simple because you still have a single writer. Now let's talk about a few special cases. Marco calls this DBMS-optimized cloud storage, but really what he's referring to here is what Aurora or LIDB or Neon are doing, which is they essentially said we'll have a more cloud-native architecture for storage that is aware of the fact that the database has these two streams of I/O, the wall stream and the data directory, and so we'll rip out the part of Postgres that is old school and we'll introduce something that's better suited to the cloud. And I think this is quite appealing. If you care about availability and resiliency, this is one of the best ways to get that with some impact to your latency, but it's not that much necessarily, and they do other optimizations to make that work well. Now, important to note that all of these are Postgres forks. You can't do this with a Postgres extension. This is really replacing an important part of Postgres, so it's not standard Postgres, but it is something that will work well from a compatibility perspective for your application. Now, active-active. I have two nodes. I can write to each of them. They talk to each other. If I write to one, it sends writes to the other one. And so I don't have to worry about there being some kind of reliability issues because I always have two writers or multiple writers. And of course, the problem is that most people would like that architecture, but they don't really think of how they need to design their application to make use of that. with Postgres 16, you can actually use logical replication to build a DIY active-active setup, because logical replication can now disambiguate between a write that's coming from the other node versus the node itself. But still, think about the problems. Think about your update statements, the conflict with each other. Today, conflict resolution in Postgres isn't really existent. It only works if your data is not overlapping between those two nodes. I would say most of the time, don't do active-active because it's going to be very painful and your application engineers won't be happy. Now, sharding and distributed SQL. Sharding is what Citus is doing. The idea behind this is that you're partitioning across servers. You're splitting up your data between the servers. Now, you still keep the regular Postgres storage. If you use the Citus extension underneath, that's still regular Postgres. You could look at any of those nodes and you'll just find Postgres, and you'll find tables with the table name underscore and then some identifier. It's really similar to regular Postgres partitioning in that sense. It just goes across servers. What Citus has done with the extension there is it made that really transparent and easy, so you don't have to think about it behind the scenes. Citus will come up with a query plan that can run across different systems, pull data across these systems, and make it work. The biggest downside here, of course, compared to single node Postgres, is that there's added latency because you have additional hops to get the data. In my experience using Citus, if you can keep data on a single node, that's always going to perform better than if you get data from multiple nodes. With the multi-tenant use case, where you have different customers on different servers, if you inform your queries of that fact, if all your queries have a customer ID attached to them, then Citus will perform really, really well and scale really well. But things start getting a little bit more complicated if you're doing a lot of queries across all the servers. You start getting into connection management issues and such. But still, this is a very scalable architecture, and I've seen many systems at scale work well with this. And now last, Marco also mentions distributed SQL. And in a sense, Marco doesn't want you to use this because this is not what he's working on. But I do think that distributed SQL has its right to exist. This is the world of Google Spanner or YugaByteDB or CockroachDB. And the trade-off you make there is that the open source solutions there, they modify Postgres quite heavily, if they're even Postgres at all. CockroachDB is Postgres compatible, but there's nothing of Postgres in CockroachDB. YugaByteDB is Postgres from a source code perspective, but heavily modified. And so you will lag behind major Postgres versions when they're released, because they have to do a lot of work to rebase their engine on top of new Postgres releases. That said, one of the things that I think distributed SQL engines like YugaByteDB can achieve better is that they actually have a more cloud-native distributed architecture, and they're actually able to handle resilience better. If one of the nodes goes down, the way that it can repair these nodes is a little bit more built into the system, I would say, versus with systems like Citus, there's a little bit more hand-holding onto the resilience aspect of that. But I do think that ultimately, both systems can work well for scaling out. And if you care about keeping things standard Postgres, then I personally would choose Citus. Overall, I would say do your own benchmarks. It depends on what's most important to you, and choose what works well in your particular workload. Thank you so much for listening. This was 5 Minutes of Postgres. Subscribe to our YouTube channel to hear about next week's episode, and talk to you next week.